Okay, welcome to week 8. I'm going to do a real quick recap of week 7's quiz. There were some issues with week 7's quiz. The first issues were actually mine, so I apologize about that. I put out a quiz and I didn't double check my numbers, and I first got an email or a text from one student saying, hey, I come up with both the current at the inductor and the current at the capacitor essentially being the same, because the two have the same amount of reactance. X of C and X of L are equal. Is that really what we're looking for? Because at that point, I've got unity. And I said, no, I screwed up. So I went ahead and I changed. I thought I had screwed up the inductor, and I changed a digit on the inductor to make it different. Well, I just made it worse. And somebody else pointed that out to me, that I actually made it so that I had a very capacitive circuit. So we can't add capacitance to a capacitive circuit and make it better. If we add capacitance to a circuit that's already got too much capacitive current in this case, then it just makes it worse as far as power factor, as far as our angle theta, which is what we're trying to do with this power factor correction. We're trying to make our angle theta smaller. We're trying to make our power factor closer to 1, and therefore our final triangle is going to look less like that and more like this. Because the closer our triangle is to that, the closer the hypotenuse is to the same length as this down here, which is usually our resistive element, depending on whether we're doing, it's the resistive current or the voltage drop at the resistor, depending on if it's a series or parallel circuit. Again, we're doing parallel circuits, so it would be the current at the resistor, and this is going to be the resultant reactive current. And of course, that resultant reactive current is one of these minus the other. Now, it doesn't matter which one I subtract from the other, but I do have to subtract one from the other. Usually I'm going to take the bigger one and subtract the smaller one from it. That'll give me a positive number. But as it turns out, we're just worried about absolute magnitude, so it doesn't matter whether you're using a positive number or a negative number, because the way we're going to use that number anyways to find the hypotenuse, mathematically it still adds out. The square of a negative number is a positive number, because something negative times something else negative ends up being positive, which is just mathematically how that works out. For our purposes, all we're worried about is what's the difference between these two? How much is there left over after I take one from the other? I had a couple of people that added them up to do Pythagorean. You can never add these two to do Pythagorean. You can never add these two to get to the triangle. Then you can use Pythagoras' theorem to solve the hypotenuse. Because if I have both of these together, then my triangle is a completely different size and shape. It has to be the difference between those two. Anyways, I screwed it up. Somebody pointed it out. I fixed it. I fixed it wrong. Somebody else pointed that out. I think Colby Abels was the one that finally figured it out for me correctly. I sat down, did the work I should have done in the beginning, and came up with a quiz, I think, on Tuesday afternoon. So hopefully most of you got the corrected quiz. A couple of you that did it before I corrected it, I went ahead and gave you full credit. You went ahead and did it the way I asked you to. You added capacitance to a circuit. You subtracted it from the inductance. You subtracted it from itself, actually, the capacitance from itself. So what you did actually wouldn't have solved the circuit, but because I put out a bogus quiz, I let it go. Everybody else who got the right quiz, most of you did it right. A few of you just stopped before you even did the power factor correction. But let's roll through this. So what I gave you was essentially this. I ended up giving you a circuit with 60 ohms here. Now again, we've got that same 120 volts everywhere, so at 60 ohms I can quickly solve that for 2 amps of current flowing in this branch. I've got 7.96 millihenries there. If I use my 2 pi fly formula correctly and put my digits in the right place, which I didn't do to begin with, my X of L should be 3 ohms. So I've got 3 ohms there. If I've got 120 volts and 3 ohms, Ohm's law tells me that I have 40 amps running through there. So I've gone ahead and solved for I, the current at L, is 40 amps. If I have 88.42 microfarads, and that's the one I originally screwed up on but didn't fix until the second fix, I do that, I should go ahead and get 30 amps. Excuse me, 30 ohms. 30 ohms at 120 volts gives me 4 amps. So I was trying to use numbers that were going to work out really easily, and I think I just made it more difficult by doing so rather than just throwing out some numbers. I was trying to use numbers that solved out to nice round numbers for you guys so you wouldn't have to worry about it. So anyways, if I dump those numbers into this first triangle, so I've got, as far as our triangle is concerned, I've got at the L 40 amps pulling in this direction. Upward is the way I'm modeling it, because it's 180 degrees to the 4 amps that are running through my capacitive branch. And my resistive branch has got 2 amps of current flowing through it. So if I go ahead and do all of that stuff, I'm going to get a I total of, I didn't solve it yet, so I'll go ahead and solve it right here with you guys. Well, I did earlier, but I didn't bring it with me. So for that, I total, well here, that's the first thing I need to do, is the thing that some of you didn't do right, is I need to subtract the 4 amps from the 40. Because as one way I teach this vector, Pythagorean math stuff with the triangles is it's like I've got a tree stump here, and I've got one strong truck pulling it that way, and I've got another strong truck pulling it that way. I think in the example it's a Ford and a Dodge. And then maybe I've got a little Honda car or a moped pulling it 90 degrees. Well, what I want to do is set this up so that that moped ends up winning, which means these two have to cancel each other out if they're pulling against each other. Well, right now they don't cancel each other out very much. I've got 4 amps of cancel against that 40, so my resultant triangle is 36 amps and 2 amps. So now I'm going to run my Pythagorean, and I got that 36 amps by subtracting the 4 amps from the 40. Since I had more inductive to start with, this is still inductive. This circuit is inductive. When we get done with it, we're going to consider an Eli circuit. L for inductance, and so the current is going to lead the voltage. So 36 squared plus 2 squared equals 1300. I'm going to go second square root, second answer on that, and I'm going to get 36.05. 05 there. So right now, if I go ahead and figure out my power factor is going to be resistive current over total current. So it's going to be 2 over 36.05, and that's going to be something terrible, isn't it? It's like going to be 5%, I think. 2 divided by 36.05, oops, 0.05, and I fat fingered my calculator, 0.5, equals, yeah, 55.48. So it's 5.5548 is my power factor, or 55.48%. Same thing, percent. If I dump that into my invert cosine just to see what my angle theta is, which is not something I asked you to do, but let's go ahead and do it just for fun. Second cosine, second answer equals, I'm going to have, that's not right, clear, second cosine, 0.5548 equals 56 degrees. So that's not very good. 56 degrees is going to be my angle theta, this angle here. That's also going to be the separation between my current and my voltage. But let's get out of there and let's go ahead to solving this for what we want to do to add a capacitor. Because what we want to do to solve this triangle is to add a capacitor, solve the power factor, correct the power factor I should say, is add another capacitor in parallel. And the question is, what size capacitor am I going to add in parallel? Well, the first thing I got to do is I got to figure out, what do I want my triangle to look like when I'm done? I want my triangle to look like some number, and I can't change this, 2 amps. I want this to be 20% or less. We're shooting for 20% of this. Now, do the quick math. What's 20% of 2? Well, let's see. 20% of 1 is 0.2. So if I double that, it's 0.4. So 20% of 2 is 0.4 amps. So that's what I want my result to be. But what do I have to do to my capacitive current to make this the result? Well, right now, 40 minus 4 is 36. And I want to get it all the way down to 0.4. I have to take out another 35.6, or I have to add another 35.6 amps capacitive to make this line longer to counteract all of that 40, except for 0.4. I'm stopping a little bit short. I'm not making it perfect in unity. And a couple people have asked about that, and it's a long explanation, and I'm not going to get into it in the videos. I'll try and answer from an email. I think Colby Clifton asked about that, and I didn't mean to ignore your email, but I have so far. For now, let's go for 0.4, because I know that if this number is 20% of this number, this is a cheat, I'm telling you guys. It's just something I know because I've been doing this a while and I'm passing it on to you rather than doing 8 more steps that the book has to get it to exactly 96 or 94 or 98. I'm saying, just make these two numbers, this number 20% of this number, and you're there. But in order to get here, I have to add some more capacitive current. And I have to add another 35.6 amps. Because if I get 35.6 amps plus 4, that's 39.6. 40 minus 39.6 is going to be my 0.4, which is what I want to end up with. Well, then the question becomes, how do I get to that number? Well, that's my X sub C that I want to, that's my I that I want to add at the capacitor. That's the current I want to flow through this branch that I'm adding. So I know that by Ohm's law, I equals E over, in this case, X sub C. We learned it as E over R, right? And so that equals 120 divided by this number, 35.6. A lot of you divided by this number. And you see why that's wrong. If I divide by this number, I'm only going to be adding a capacitor that gives me that number. And that's skipping a step. I need to add a capacitor that gives me this much current in order to subtract it from the inductive current to get to this number. Now, I'd say about 70% of you did this step right, and about 30% of you did it wrong. So don't feel like the lone stranger if you did it wrong. I understand where you were coming from. But just know that you actually need to use this number that gets you there. So 120 divided by 35.6 is going to give me some other number, which is going to be my, let's see, did I do that wrong? 120 divided by 35.6 equals 3.37 ohms. So I actually did do that wrong. I'm actually, because I've got current, I need to solve X sub C. So the formula I put up worked, but I put it up there wrong. It's E divided by I. So that's not the formula. This is the formula I wanted, because this is current I'm putting in here, right? And that's X sub C that we're solving for. So bear with me, doing this as I go. So X sub C equals E over I equals 120 divided by 35.6, and that gives me my 3.37 ohms. So that's going to be the X sub C I'm looking for, is 3.37 ohms, right here. Now, I can't buy a capacitor by its X sub C. I have to buy a capacitor by its capacitance. So from that number, we need to pull out its capacitance, and we know that by finagling that formula X sub C equals 1 over 2 pi fc, that I can get an equally valid formula is C equals 1 over 2 times pi times frequency, which in this case is 60, times X sub C. So run those numbers through. So let's do that really quickly, because I didn't take my notes with me. 2 times pi times 60 times X sub C, I decided was 3.37, equals this big number, but I have to invert that number because I have 1 over it. So this is how I do it. I do everything first, and then I just invert the answer, and I get 0.000787. 0.000787. Well, I know that if I pull those 3 zeros out of there, the rest of it is microfarads. So I've got 787 microfarads that I need to add here. I need to add a capacitor that's roughly 787 microfarads in capacitance. And that will then give me my 0.4 here, because that'll add another 35.6 amps there. These two add together. Remember, capacitors in parallel add, and the current in any parallel circuit adds in the two. Since they're both capacitive, they are in phase with each other. Remember, their current is 180 degrees out of phase with the inductor. Their current is 90 degrees out of phase with the resistor, which is why Pythagorean works. But they're together, so we can just add them up. So the 4 amps plus the 35.6 equals 39.6. Subtract that from the 40, and I get my 4 amps. My 4 amps and my 2 amps now should give me something closer to 98. I'm going to erase some of this and do that math really quickly. 4 amps and 2 amps. I've showed you how to do that. So the way I do that to solve my hypotenuse here is I go 0.4 squared, forgotten where the squared button is, plus 2 squared equals some very small number. I take its square root, enter, whoops, I get a syntax error, second answer, and I get 2.03 amps. So my total current on the system is going to be 2.03 amps. 2 amps of that is my resistive current. So that's going to be a really good power factor, right? In fact, I can solve it. It's 2 over 2.03. So let's see, 2 divided by, second answer, and my calculator is going to be giving me 98.9805, or 98% power factor. If I go ahead and dump that into my invert cosine, just to see what my angle theta is. My angle theta is only 11 degrees. So now this little angle is only 11 degrees. So what I've effectively done is I've moved a sine wave that looked like this, right? And it was like 55 degrees, so here's 90. So here was my old 2 sine waves. A lot of distance between those two. And the farther apart the current is from the voltage, the less power, the less true power you're getting out of this, because you're only getting true power when those two are both in the positive. So while one's in the negative, like right here, everything from here to here, I'm getting power. I'm getting true power out of that. But when one's in the positive and one's in the negative, like if I use a different color here, all of this, I'm not getting true power out of that. So I've got current that's flowing. I'm paying to push the current through, but I'm not actually getting anything out of it. Again, where they're both negative, I'm going to have true power there. But a lot of this circuit, I'm not going to have true power. What I've done is I've moved that to look more like this. At only 11, use the correct marker here, at only 11 degrees, there's one of my sine waves. Again, here's 90, here's 45, here's 22, right? So here's 11. Really close to each other. So now the lion's share of this circuit is going to be true power. And it's only going to be this tiny little area here, and I drew it poorly, this tiny little area here that I've got power that I'm pushing current through a wire to get power that I'm actually don't have any use for. That I'm not getting true power out of. So that's one of the reasons that we correct power factor, is to get it to there. The things that people screwed up on were subtracting these and also using this number as the current to solve for x sub c. They didn't do like I did and wrote the wrong formula up. But you solve for x sub c, and with the x sub c, you solve for the capacitor. So I figure out what my current is by what more I need to add here. I need a branch with that much current. I figure out what's left over, what capacitor I need to add. I solve for that capacitor's x sub c with the current by dividing it by the voltage, Ohm's law, and then I use the 1 over 2 pi fc formula, but I change it to c equals 1 over 2 pi f times x sub c to solve for the capacitance. And then I can go to the capacitor store and say, hey, give me this size capacitor to add to that circuit. That's kind of the long way around. Honestly, this is like 9 steps shorter than the way the book does it. So if you want, take a look at how the book does it. We're not going to test on this anymore. I just want to make sure that any of you that didn't get it had a chance to understand it if you wanted to. You may work a whole successful career as an electrician and never need to do this. You also may find that it is crucial to getting that really good big job doing some electrical design when you're assigning supervisors. So it's not bad stuff to know. It's really good to understand the nuts and bolts of what we're working with as electricians every day. And this is a big part of it. So a lot of people have said to me after my class, and other instructors even have said to me, you know, I don't need a lot of this. I'm never going to use this. And I'm like, well, you may never need to use this. You know, I know great electricians that go their whole careers without ever bending a piece of pipe. But it's sure good to understand how to do some pipe bending. I know good electricians that are never ever going to wire a 3-way switch because they don't work in that sort of field. But it's still good to understand how a 3-way switch works. This is the same sort of thing. It's really good to understand this stuff. I hope that those of you who needed to watch this video did. I'm going to put it up and say only the folks really that want to see it need to do it. I'm going to do another video presently on for week 8, the actual lecture for week 8. But hope that helps and didn't harm.